Hello everyone, welcome back. In this video clip, I'll go over two types of functions that you guys are going to see in our course. They are exponential functions and logarithmic functions. Okay? Let's start with the exponential functions. Exponential function. The exponential function is a function where the variable x is on the exponent. Okay? So in general, people define this way: f of x equal to a to the x. All right? Pretty much that's the definition. Let's box that. Where x, of course, the inputs of the variable, and a is called the base number. Okay? A is not equal to 1, and a is positive. Those are the two conditions for the base number. You guys see why? What if a equal to 1? And 1 raised to the x is just simply equal to 1. It's not exponential anymore. Or if a equal to 0, same thing happened. A is negative, then we haven't learned about negative number raised to some random variable x yet. So we rule out that case. We only talk about positive base different from 1. And that was our definition. Example. Say f of x equals to, say, 2 to the x. All right? In this example, base 2 to the x. Or say f of x equal to 1/2 to the x. That's another exponential function. Base could be anything as long as that number is positive and different from 1. 1/2 obviously positive, and 1/2 obviously not equal to 1. So you're good. Or you can even have like f of x equal like pi to the x. Is that okay? Yeah. Because pi is a constant. Pi is equal to, approximately equal to 3.14159. So should be good. And then we can extend the concept a little bit more. And if we have some knowledge about transformation, we can even shift that function, shift the graph up, down, left, right. We can have something like this. Say f of x equal to, say, 2 to the x, and then say -5 right here. The graph will be shifted down 5 units. Plus 3 right here. What? Move to the left, 3 units. You can even multiply 7 right there. Okay. So the original functions, I think, is stretched out by, first of all, this one, stretched out by this one right here. Stretched out by a factor of 7, I think, and then shift to the left and then shift down. Okay. Of course, they are called the exponential function. Okay. So the definition is not too hard. Just variable x is on the exponent, and you don't even need to have a single x. You may have more complicated things on the x. Say f of x equal to, well, I don't have to change that. How about this one? 3x squared plus 15x minus 7. That's okay too. That's still an exponential function. Okay, as long as the x is on the exponent. You're good. Now, let me go over some basic properties of the exponential function. And let me bring the properties to you via graph. By looking at the graph, we're going to observe some properties of the exponential function. Okay. So the first example, how about the one that we just read? F of x equal to 2 to the x. Okay. So the graph going to be like this. X-axis right here, y-axis, the origin. Graph going to go up quickly this way. All right. By looking at the graph, we can see some property. This is 1 right here. Okay. Look at x equal to 0, 2 to the 0 is 1. Right? The domain, whenever you guys hear the word domain, think of the x dollar. X traced along the graph is what people used to see. All the way from negative infinity to positive infinity, in other words, all real numbers. Okay? The range, it's not all real numbers anymore. It could go all the way up infinity, but When it goes down, always above the x-axis, so always positive. The range is a positive number, 0 to infinity in parentheses, okay, not including 0. Okay. More probably, you see that the graph will never change direction, right? Always going up. Let's see what the function is increasing. Increasing. Okay. Increasing means what? The bigger value of x, the bigger value of y. You plug in the bigger values, you get back a bigger output. That's what I'm saying. All right. And of course, decreasing is going to be the opposite of increasing. Now I'm going to talk about a very important property that is going to be very useful for your learning. And if we heard that quite a while ago, it's a good time to bring it back. You heard something called the one-to-one function. Okay, so let's start. Function. What does it mean by a function? Function is a relation between the input x and the output y. So you assign some value for x, you plug in, the function follow the rules of recipe, going to give you back the output. Okay, so this particular function, what? You plug in x equal to 5, do what? 2 to the 5th, you give you 32 back out. Okay, that's a function. Okay, and the function is going to satisfy one condition. What? For each input x, you can only get exactly one output y. Each valid input x, you're going to only get exactly one output. Okay, and we have a test for that graphically. We call the vertical line test, right? And you say what? If there's a graph that intersects a vertical line at 2 points or more, and at some point, then it's not going to be a graph or function. Okay, if it's a function, then it doesn't matter where you draw the vertical line. Always intersect the graph at 1 point or less. Okay, now we have another test called the horizontal line test. It's very similar. The idea is very similar to the vertical line test, but this horizontal line test is used to test for something called one-to-one function. And what does it mean by one-to-one function? Keep in mind that in the definition of function, we never restrict the condition for the input. We only restrict the condition for the output. Each input can only give you exactly one output. But two different inputs can give you the exact same output, and that's okay. That's still a function. Say something like y equal to x squared. You plug in x equal to 3, you got 9 out. You plug in x equal to negative 3, you still got 9 out. See, this is a function. 3 in, 9 out. Never get anything other than 9. Negative 3 in, still got 9 out. Never get anything other than 9. So that was a function. But this function is not one-to-one. Okay, because you can have two different inputs give you the same output. We learned a very special type of function we call one-to-one function. It means that we will restrict the condition for the input as well. It means that different input cannot give you the same output. Different input gonna give you different outputs. And if a function satisfies that condition, we're gonna call that function a one-to-one function. It's like one in, one out. Okay? And we have a test for one-to-one function. It's a function already, keep it in mind. One-to-one, this function gonna pass the horizontal line test, and same idea as the vertical line test. If you have a function and it passes the horizontal line test, and you say that the function is one-to-one. So this one is really a one-to-one function. How about parabola? This parabola is not a one-to-one function because I can draw a horizontal line that hit the graph at 2 points. Okay, you see, y equal to x squared. You have two values of x, give you the same value of y. So the next question you may ask is, why do we need one-to-one function? Because after this, after the one-to-one function thing, that you guys learn something called the inverse function. Okay, and only one-to-one function can give you the inverse. Why is that? Say 1 in, 1 out, and you can flip around. You have 1 in, 1 out again. Say a function that got 3 in, 5 out. And you can find another function of what? 5 in, 3 out. That's called the inverse function. If a function is 2-to-1, 2 in, 1 out, the other way is going to be 1 in, 2 out. It violates the condition of the function. So it's not okay. That's why we need one-to-one function. Okay? And I claim that if a function is one-to-one, if a function is increasing, say it's going up all the time, for sure it will be one-to-one. And if it's one-to-one, then you can have the inverse. And that's important because we cover two types of functions today. Exponential function first, and guess what? The inverse of exponential function will be the logarithmic function. Or in short, we just call it log function. Okay, so increasing is going to be 1 to 1. By the way, this is notation for 1 to 1. Okay. Another problem that I see in this graph, for this particular graph, for this particular function, exponential, it has an asymptote. The asymptote is the line, right? Where the graph is getting closer, never intersect at infinity. Could be intersect somewhere in the middle, but when you extend it forever, then the graph just simply getting closer to that horizontal line, but never hit it. And we have the horizontal asymptote in here, which is the x-axis. The equation of x-axis is y equal to 0. The x-axis. All right. Out of ink. Now let me give you another example, and I'll talk briefly about the second example because it's similar, except for one thing. In this example, I give you a base a equal to 2 right here, which is positive. More than that, it's bigger than 1. The second example, I'm going to give you this f of x equal to 1/2 to the f. It is still an exponential function, but this time the base is 0.5. In other words, 1/2, less than 1. Still positive. And see this, the graph going to look like this. This is the y-axis still, this is the x-axis still. Make it shorter, have some more room to write. And then the graph, red color, it's going to look like this. Okay. See 1 right here, and 0 right there. All the probability carries over except for the monotonicity probability. It's not increasing anymore. It is decreasing. Right down here, domain still negative infinity to positive infinity. The range 0 to infinity. Okay, decreasing. And of course, still 1 to 1. That's the horizontal asymptote at y equal to 0, which is the x-axis. Okay, this one's out of ink too. So pretty much you guys see some basic properties of exponential function. Alright? And there's a lot of application, a lot of use that involve an exponential function. One of the application that all of you guys have seen before, the compound interest formula. Let me write somewhere down here. The compound example. Called the compound interest formula. You have what? PT is equal to A times, AT, I wrote backward. I just try to match the letter with what you see in the book. P times 1 plus R over n, everything raised to the power of n times t. This is called the compound interest formula. So you got the exponent right here. T, the variable now is not x, t. T stands for time, by the way. Is the variable on the exponent. And what is it talking about? Money. You have a principal amount P, say $5,000, and you want to invest in some kind of saving account or some kind of investment that yield the interest of R right here compounded monthly or weekly or annually, in general, periodically. Okay? And this formula will help you to calculate how much money you have at the end of the year. Say, if the interest is 12% compounded monthly, then R here is going to be 0.12. Keep in mind, we always have to convert percentage to decimal before we calculate the math. And then 12 compounded monthly means what? The interest is calculated 12 times a year. You plug in n equal to 12, okay, n equal to 12, and if you put it in 1 year, then t equal to 1, and if you want to invest your money for 5 years, and t is 5 years, and 5 t, whatever the number of years plug in there, could be decimal, and you plug in in the formula you have the future amount of money after time t of a couple years. And if you compare your interest like weekly, then n is weekly, how many weeks a year? 52, right? And daily, 365. Some books use 360 for compound daily, and that's okay too. It won't make a big of a difference. They calculate 30 days a month, so 4 months is 360 days, and that would too. Okay, and then eventually you're going to come up to something that's the interest compounded continuously. Another word, and later on when you learn about limit and take n go to infinity, and the whole thing right here is like e raised to the r. So p times e to the rt. That's the compound interest formula that compounded continuously. But anyway, just trying to bring you an example of the use of the exponential function, and you will see more examples about what growth and decay, right? Half-life. Right? One example to come back. And in here, I'll just try to show you basic properties. Focus on this more than the use of the application of the exponential function. Too many applications to talk about this sum. All right. Now let me move on to the logarithmic function. In short, let me just call it log function. Okay. And as I claimed a minute ago, log function is the inverse of the exponential function. So the question is, how do you find the inverse of a function? I'm trying to save the graph. Let me erase that right here. The inverse function is a new function that flips the rows of the input and the output from the original function. In other words, say if you have the original function right here, y is equal to 2 to the x. Okay? So x, think of x as the input, think of y as the output. Right? One in, one out. It's 1 to 1. It's good, right? Now we're gonna interchange the rows of input and output. So x becomes y and y becomes x. You have a new function. X equal to 2 to the y. And this one right here, the new one right here, is exactly the inverse of the original one. Okay? However, we have the function y on the exponent, and it's kind of hard to do the math with. So we invented a way of representing this function, and we denote the function this way: y equal to log base 2 of x. Okay? And with this writing, we define this is exactly the meaning of this one. This means 2 to the y equal to x. So 2 right here is the exponent. And y here is, I'm sorry, 2 here is the base, I said it wrong, base. And y here is the exponent. Okay? So let me give you the definition of the log function and move on from there. I tried to save the graph to show you the exponential, but there's some room to write, so sorry. Let me give you a definition, and then we're going to redraw the graph. Okay, definition of logarithmic function. Logarithmic function. Okay. A log function is a function that looks like this. F of x equal to log base a sub x in general. Okay. Now let's box that. Make it stand out. Okay. Where a here is called the base number, and a has some conditions. A gonna be different from 1. A gonna be positive, exactly like what you learned from the exponential function. And what does it mean by that expression, the log expression? Where I need another black marker. Y equal to log base a to the x really means, this expression means what? If you take the base number right here, you raise the exponent y right here, it's going to be equal to a number inside the log. Means what? A to the y equal to x. That's exactly what it means. All right, so let me give you some examples. Make sure that you guys get the hang of the log function. Example, if I got 3 is equal to log base 2 of, say, x minus 5. And what do I mean by this? The base is 2. The exponent is 3. And then 2 raised to the third power is going to be equal to x minus 5. And this means 2 to the third is equal to x minus 5. Okay? I'm not trying to solve it, just trying to show you what it means by the log notation. What if you have something like this? 3x plus 1 equal to log base 11 of 3y squared minus 2y minus 4. And what do we really mean by this? It means that 11 is the base number raised to the exponent of 3x plus 1 equal to 3y squared minus 2y minus 4. That's all we're trying to say. Okay? And keep in mind that the base number is going to be a positive number and it's different from 1. Same base with the log function. All right. There are 2 common bases that we've been using a lot for log function. It's called base 10. Log base 10 of x. And since we use it a lot, we try not to write base 10 anymore. We just simply omit it. We write it this way, log x. And if you don't see the base number, you understand that people implies base 10. The second base that we use a lot is base e. Log e of x. And instead of e is the number of natural a constant, okay? And instead of write this way, they write this ln of x, where e is a constant, just like pi. E is 2.71828. 1828 another time. 5 decimals good enough. Okay. And denoted by ln. E equal to 2.71828. Okay. Those are the 2 bases people use a lot. I claim that I may be wrong on that. Correct me if I'm wrong. Previously, people tend to use base 10 a lot, but recently, I think no, quite a while. Okay. Since number e that's found, and we find that e natural log of the log base e seems better to use, and people tend to use base e quite more than base 10. You can use any base you like as long as it's positive and different from 1, then we're good to go. Okay. Now I'll show you some basic properties of the log function, and you see why I try to keep the graph of the exponential function. Let me redraw the graph of the exponential function right here that I'll just erase because I didn't have enough room. This was the graph of the exponential function y equal to 2 to the x, right? Okay. And the origin right here, 1 is right there. Now I'm going to talk about the inverse of that function. The inverse of y equal to 2 to the x will be x equal to 2 to the y. And we learned about the log notation already, so we're going to write it this way. Y equal to log base 2 of x. See? 2 to the y, 2 to the y equal to x. Okay. And let's take a look at the graph. How about green color then? The graph going to look like this. All right. We use green color for all the problem. The domain is 0 to infinity. The range is for the y value from negative infinity to positive infinity. Increasing, yes. Increasing 1 to 1, of course. Got an asymptote. Now it's not the horizontal anymore, it's vertical asymptote. At x equal to 0, which is the y-axis. Okay, right here. Pay attention to this. C1. The domain of the log function is really the range of the exponential function and vice versa, because basically we are just interchanging the roles of the input and the output, right? See, for the exponential function you have horizontal asymptote y equal to 0. Now it becomes a vertical asymptote x equal to 0, right? So x becomes y, y becomes x. Okay, and another one. Look. Take a look at this line right here. This one, the diagonal line, the dotted blue diagonal line right here, we call it the bisector. Okay, this bisector split the quadrant number 1, quadrant number 2 into 45-degree angles. Okay, and imagine that if you kind of fold in the graph along the bisector, then the exponential function and the graph the exponential function and the graph the log function kind of line on top of each other, because pretty much we're interchanging the roles of x to y and y to x, right? Folding along that line, the x-axis now on the y-axis, and the y-axis now becomes the x-axis. The graph is symmetrical along that bisector line. Okay. Over here, the second example, we use y equal to 1/2 to the x as the exponential function, right? Now inverse is going to be x equal to 1/2 raised to the y, and of course we're not going to write this way. We're going to use the log notation, so y equal to log base 1/2 of x. All right. See, base to the exponent equal to whatever inside the log. All right, keep that with you. We study math from definition. Okay, let's take a look at the graph. And the graph of this one is going to be like this. Okay, the green curve is a graph of the log function. And same probably as you have before, but we should not just write it down here, except for one thing. Same domain from 0 to infinity as this graph right here. The range is still negative infinity to positive infinity, and the graph is not increasing. This time it's decreasing. Still 1 to 1, still have a vertical asymptote at x equal to 0. And if I draw the bisector line, and the graph still symmetrical about the bisector line. Okay. So we are. This video clip today, I try to bring back some very basic properties of the log function and the exponential function. This is a curve, and it's either increasing or decreasing, never change direction. And of course, it's 1 to 1, therefore it's going to have an inverse function. And inverse of the exponential function is a log function, and vice versa. Okay. And next, I'm going to show you some formulas, some basic formulas. Recall some, I bet that you guys know this already. Just rewrite them. Just bring it back to you. Refresh your mind. Okay. Exponential formulas. Exponential formulas. Let's call A is the base, okay? The base A is the not equal to 0. So we got a to the 0 is equal to 1. Right? A to the 1 is just A. Right? A to the n times A to the m is equal to A to the n plus m. You multiply two numbers with the same base, then you have a new number with that base, and you add the exponent together. A to the n over A to the m is A to the n minus m. Multiply becomes adding, divide